We defined the problem by asking for the limit of the sequence 1 plus 1 over n, all raised to the power of n, as n approaches infinity. To address the variable exponent, we recall the power property of natural logarithms, which states that the log of a base to an exponent equals the exponent times the log of the base. Applying this property allows us to bring the exponent n down as a coefficient, rewriting the expression as n multiplied by the natural log of the quantity. We formally assign the variable L to represent the original limit we are solving for. Taking the natural logarithm of L, we equate it to the limit of our transformed expression, n times the natural log of 1 plus 1 over n. To prepare for calculus operations, we rewrite the multiplier n as the reciprocal of 1 over n, transforming the product into a quotient structure. This substitution allows us to express the natural log of L as the limit of the logarithmic term divided by 1 over n. Evaluating this fraction as n approaches infinity results in a numerator and denominator both tending towards 0, creating an indeterminate form. This specific condition authorizes the application of L'Hopital's rule, which asserts that the limit of a quotient of functions equals the limit of the quotient of their derivatives. We therefore proceed by setting up the derivative of the numerator with respect to n divided by the derivative of the denominator with respect to n. Differentiating the numerator requires the chain rule, multiplying the derivative of the outer logarithmic function by the derivative of the inner function u. We identify the inner function u as the term 1 plus 1 over n. Calculating the derivative of u with respect to n yields negative 1 over n squared. Combining these components via the chain rule gives us the reciprocal of the inner function multiplied by its derivative. Algebraically simplifying this product results in the concise fraction negative 1 over n squared plus n. We now address the denominator by applying the power rule for differentiation to the term 1 over n, which is n to the negative 1. This derivation confirms that the derivative of the denominator is negative 1 over n squared. Substituting these results back into our L'Hopital's expression, we obtain a complex fraction of the simplified numerator over the simplified denominator. We resolve the complex fraction by multiplying by the reciprocal, which simplifies the entire expression to n squared divided by n squared plus n. To evaluate the limit, we divide every term in the fraction by the highest power n squared, yielding 1 over 1 plus 1 over n. As n approaches infinity, the fractional term 1 over n vanishes to 0, leaving us with 1 over 1 plus 0. This calculation simplifies directly to 1. We have now established that the natural log of L is equal to 1. To solve for L, we apply the inverse logarithmic property, exponentiating both sides with the base e. This operation isolates L, showing it is equal to Euler's number raised to the power of 1. Thus, we conclude that the limit of the sequence converges exactly to the mathematical constant e.